Hello, this is Captain Chaudhari in my series of videos on basic stability calculations. I was doing the application of moment of inertia. Today I am going to do the application of moment of inertia to find out what is the free surface moment of a tank, that is curvilinear, right? So we are going to see like how the moment of inertia influences, how the moment of inertia gives us free surface moment in case of a tank whose dimensions are given. Earlier we had done a video on free surface correction. The free surface correction that is caused by a tank depends on the density of the liquid, depends on the transverse extension of the tank, depends on the area of the free surface rather than the capacity of the tank. That means if the tank is half full or 1/3 or 2/3 full does not make that much of a difference. This means that rather than the capacity of the tank, what is the horizontal extension of the tank, right? How much liquid, suppose the liquid goes to and fro in the form of a wedge, like what is the size of wedge and what is the transverse extension through which the wedge is transferred, because this transfer of wedges is going to cause transfer of center of gravity of the ship. In a very simple explanation, suppose we say that here's the ship, this is the center of buoyancy and this is center of gravity, and let us say here is a tank where the liquid is partly filled, where the liquid goes to the starboard and then goes to the port, and this wedge of liquid is going to and fro. This swing of the wedge which goes to and fro as if the swinging point is here. So effectively this wedge, the weight of this wedge is considered at this point, and this also has a corresponding effect on the ship whereby center of gravity of the ship goes to and fro, and as if the swinging point of the center of gravity is over here. This is the virtual rise of G. So basically, when I ask a candidate what is the effect of the free surface, he says virtual rise of G or virtual loss of Gm. This is virtual rise of G. Actually, G does not go up. Actually, G effectively is in a higher position. That is called virtual rise of G. So effectively, what happens is the righting capability of the ship reduces because the Gm reduces. So if somebody asks you like what happens because of the free surface, where does the G go? G goes actually sideways, and the effect of G going sideways is to reduce the righting capability of the ship at every angle of heel. So the effect is as if the G has not gone sideways, G has gone upwards, because by G going up, once again the effect is reduction of righting capability. So let's do this question from my book. It says that there is a diesel oil tank, on the center. This is a plan view we are seeing from top, right? This is the center line, and this diesel oil tank is on the starboard side, and one side is flat, another side is curvilinear, and these are the dimensions 7.9, 5.2 and 2.8, and you can see that like in calculating the free surface effect, we always have an axis. This is the center line of the ship, right? If you imagine an axis which passes through the centroid of this tank free surface area and parallel to the center line, this axis is parallel to the center line. So if we have moment of inertia with respect to this axis, which is parallel to the center line and passing through the centroid, that is what will give us moment of inertia, or that moment of inertia multiplied by the density of liquid will give us free surface moment. So always in a situation where we have to find out the free surface correction or moment of inertia, we always take an axis which is parallel to the center line of the ship, right, passing through the centroid, which means that this is the reference axis, original reference axis, and the ordinates are perpendicular to the reference axis. So when the ordinates are perpendicular to the reference axis, and what happens, it is a 5-column format. This 5-column format will help us to find out where is the centroid of this area and what is the moment of inertia about an axis which is the flat side axis, and we can transfer this moment of inertia to another axis which is passing through the centroid. Let's do this question. So in the first column I'll write down the ordinates y, and that is 7.9, 5.2 and 2.8. Now this tank is 9 meters in length. This is the 4.5 dimensions, 9 meters. That means the value of h is 4.5. Now Simpson's multiplier will be 141. Y dx, that is the third column for the area, 7.9, 20.8 and 2.8. The total is 31.5. The next column is for moment of area, and y dx multiplied by y will give me y square dx. So 7.9 multiplied by 7.9, 7.9 into 7.9 gives me 62.41, 62.41. 20.8 into 5.2 gives me 108.2, 108.16, and 2.8 into 2.8 gives me 7.84. The total would be, it gives me 178.41, 178.41. And the last column is for y cube dx. That is for moment of inertia about the flat side. This column is for moment of area about the flat side. As you can see on one side, the termination of the ordinates is on the flat line, and the other side is curvilinear. We get moment of area or moment of inertia about the flat side. So y cube dx means the product of this column and the first column. So that is 62.41 multiplied by 7.9 gives me 493.04, 108.562.43 gives me 21.11, 21.11. So $1076.58. So let's find out the area. Area would be h by 3 into sum 1. H is 4.5 meters divided by 3 into sum 1, that is 31.5. So that is 1.5 into 31.5 gives me 47.25 meters square. 47.25 meters square. Moment of area about the flat side will be 4.5 upon 3 into sum 2, that is 178.4 multiplied by half. Half is part of the constant that has to be multiplied when we want to find out moment of area when the ordinates are perpendicular to the reference axis. So it is 4.5 into 178.4 equals divided by 6. That gives me 133.8 meter cube. So 133.8 meter cube is the moment of area about the flat side divided by area divided by 47.25 will give me the position of centroid with respect to the flat side, that is 2.832. So if this is the centroid, this distance is given as 2.832 meters. Now next I'll find out what is the moment of inertia of this area with respect to the flat side. So that is 1 upon 3 into h upon 3, that is 4.5 upon 3, multiplied by something, that is 1076.58. This 1/3 or 1 upon 3 is a regular constant which we need to multiply with in a situation where the ordinate is perpendicular to the reference axis. So this is 38.3 meter raised to 4. Now this is the moment of inertia about the end axis, that is the center line of the ship, but I want moment of inertia about the panel axis which passes through the centroid. So the moment of inertia about 4.5 axis, right, through centroid would be 538.3 minus AD square. Area is 47.25 and D square means 2.832 square. Let's do it. 2.832 into 2.8323 gives me 159.3. This gives me 159.3 meter raised to 4. And free surface moment, as you know, is moment of inertia which we have found multiplied by the density of liquid. The density of liquid is 0.82 tons per meter cube. So this multiplied by 0.82, that gives me 130.66 tons meter. That is the free surface moment. So this is how we find out the free surface moment that is contributed by a tank. In many stability booklets, the moment of inertia that is provided by a tank, through an axis which is parallel to 4.5 axis and passing through the centroid is given in the tables. So whenever we are picking up that moment of inertia information from the table, we must multiply with the density so that we get the free surface moment.